Thank you. So back when I was 20 years, that was in 1992, I started to study computer science, and that was the first time I really, saw the internet, and things you can do there. And there was FTP, so you could download files, and there was, mail, so I could mail somebody on the other side of the planet if I knew somebody over there. And there was Gopher and news groups and all sorts of things. But what I was then thinking about is that we don't really have any money on the internet. And well, a few years later, we got the web, and then we could use credit cards eventually for paying over the internet. But that's kind of a hack. Credit cards were never really meant for that. So you write down this number, and then the expiration date, and then your name. And on the flip side, eventually there was added this other number. But that was, in my mind, a hack. So I was really looking for something which is like real value that you can transfer digitally. So fast forward to 2011, I heard from one of my colleagues that there's this thing called Bitcoin, and I immediately jumped into it because I found that, well, maybe this is the answer to the thing I've been looking for so long time. And basically, I found out that, well, this is just super interesting, so I just had to spend all my time looking into that. And basically, eventually today, I am a co-founder of a company that actually catches bad guys using Bitcoin. But that's a different story. So today, I would like to tell a little bit about how Bitcoin actually works. So in the media, we hear a lot about Silk Road and drugs and exchanges crashing and things like that. So this talk is not at all about these things. So I would like to explain, so how does it work? And this invention that is behind Bitcoin, is that something we could maybe use for something else? So another thing is that normally Bitcoin is pretty complicated. I will go through it really quickly. There will be some corners where I'm just not going into full depth because we can't manage all of it. And basically also normally I say that, well, the first 3 times you think you understand how it works, you are probably wrong. At least that's the experience that I went through when catching up on it and reading about it. So maybe after this talk, you will only have to be wrong 2 more times or something. Okay, so this talk is not about the political or economical impact of Bitcoin. That's a whole different topic. So it's not about how you buy and sell or spend or secure your Bitcoin. It's about how it actually works. And basically, let's just start with the beginning. So it all started in 2008 when somebody calling himself Satoshi Nakamoto published a white paper on a crypto mailing list. And the white paper was called Bitcoin, a peer-to-peer electronic cash system. And this kind of solution that he advertised for here was something that people have been looking for a long time. And along comes this nobody who nobody heard about him before, and he claims that he had solved it. So this was largely ignored. And then 3 months later, a working implementation was published, and the Bitcoin network was started. So before we go into the actual nitty-gritty details, so a little bit of history of what happened in Bitcoin. So basically, the first transaction was sent in January 2009, and the first kind of real monetary transaction happening, at least the most famous one, is somebody buying 2 pizzas for 10,000 Bitcoin. Then 2011, a Bitcoin was $1 US. And then somebody bought a Cessna aircraft for 10,000 Bitcoin, so the equivalent of 2 pizzas. And then the price rose, and eventually at the end of 2013, the price crashed, and then it settled down into 240. And today, 1 Bitcoin is about 750 dollars. So there's been some ups and downs. Personally, I haven't been tracking all of this, the price going up and down. I've been more interested into the technology that's behind it. So, so what is Bitcoin? Well, it's many different things. So first of all, it is the name of a peer-to-peer protocol. So this is the protocol that the computers who are participating in the Bitcoin network, that they use when they communicate with each other. So Bitcoin is also a unit of account, just like euro or dollars or World of Warcraft gold coins. And it's also a payment system, so you can send value between accounts in the Bitcoin network using the Bitcoin payment system. So when we talk about payment systems, so we already know some of them, right? So we use them every day. Like I use my Visa card when I buy something online, for instance, or PayPal, or for instance when I play World of Warcraft. I'm also using a payment system where I pay with World of Warcraft gold. So in these payment systems, we have some properties. So one is that, well, you can't counterfeit money. So I can't go into World of Warcraft and then increase my supply of gold coins just like that. I can't, put more money into my bank account without actually paying something for it. Right? And also, I can't double spend. So if I have bought a pair of shoes, then I can't buy a pair of trousers for the same money. So I can't double spend. And also, transactions, I can't really reverse them. But the thing is that I can't, but somebody can in traditional payment systems. So there is some central point where you can go in and then do these things. So for instance, I can tell Visa that, well, I didn't get my pair of trousers, so can you reverse that transaction? And then Visa can decide, yeah, we will go ahead and do that, and then withdraw that money out of the merchant's account, and then eventually send it back to me. So somebody can reverse transactions. Also with double spending, so someone can do double spending, and actually it happens all the time in our modern banking system. So if I deposit $1,000 into my bank account, then the bank can lend out $900 to somebody else, and now we have created money out of thin air, right? And so basically banks, they can do that, but I can't. And the same with counterfeiting. So I can increase the money supply at will, but the national bank, they can if they want to. And this is partly how inflation is done. So with Bitcoin, it's a little bit different because nobody can increase the money supply at will. So because Bitcoin is governed by some rules, mathematics and cryptography. So you can't just go ahead and create more money. And the same way with transactions, you can't reverse them. There's no place where you can go and say, now I want to reverse this transaction. And again, with double spending, you can't just go ahead and spend some coins that you have already spent on something else. There's nowhere where you can go and say, well, I want to change stuff. So basically, so I'll try and explain how these three properties, they come along. So basically, Bitcoin solves at least two things, a number of things. So I want to focus on those two, which I think is most important to how it really works. So one is that it eliminates trust in a central authority. So what you do is you trust the rules of the protocol, and the protocol is software running on thousands of computers on the internet, and basically all the rules are described in mathematics and cryptography. So there's no political thing to trust. It's just the code. And then another interesting thing that Bitcoin solves is the distribution of funds. Because if you create a new currency, so how do you get money into this system? Because if somebody has all the Bitcoins in the beginning, then you have to distribute them somehow. And that's a central point, right? So, and we don't want that. We want to avoid all central points. It has to be totally distributed. So let's talk about this distribution of funds first. So basically, the way it works in Bitcoin is that every 10 minutes since the Bitcoin network started, there's basically a random node in the Bitcoin network. It receives a reward. And that reward started at 50 Bitcoins, and the reward halves every 4 years. So basically, the first 4 years, you had like 50 Bitcoins every 10 minutes, and then the next 4 years, it was 25. And that gives us this distribution, where we, in the beginning here in 2009, we got these 50 Bitcoin, and then the next 4 years, we actually sent half of the value into the network. And then the next 4 years, we sent the next 25% of value into the network. And eventually, it flattens out and goes to 0 in 2143. So, and that's all nice, right? And there are some incentives here, right? If you join the network early, then there was an incentive to join early, because then you would maybe get some more rewards and so forth. And if I was an economist, I would also begin to talk about deflationary currencies and things like that, but that's not the topic of today. So, but it's all nice to say that, well, we do it like this, right? But how do you enforce that in a network where nobody, trusts each other? It's just, software. And to explain that, I have to explain first the fundamental invention in Bitcoin, which is the blockchain. So the blockchain is basically the layer that Bitcoin is built on top of. It's a database that contains all the transactions that ever happened. So when I send a transaction to the Bitcoin network today, it is then recorded into the blockchain, and it's kept there practically for eternity. And every full node in the network, they have a copy of this blockchain. And they keep it up to date with new blocks as they are found and appears in the network, verifies that everything is good and sound. And then some of those nodes, they work as what we call miners. So they extend the blockchain with new blocks. So the blockchain started with block number 0, the Genesis block. And that block is part of the software. And it was created by Satoshi, and contains actually the title of an article from the Times, because this proves that this data didn't exist at some earlier point in time, which is important. So basically, the blockchain is a large linked list consisting of, today it's something like 440,000 blocks. And you can think of it as a big accounting book. So every page in the book, or every block is a page in that book, and anybody can try and add a new page to the book, and if you do so, then you get a reward. So this reward that happens every 10 minutes. So, but how do we then do that? So how do we make sure that something only happens every 10 minutes on average in a distributed network? So to explain that, I want to introduce a cryptographic hash function. So SHA-256 is what is called a cryptographically secure one-way hash function. So what you do with that is you can take any binary input, and then you produce 32 bytes of seemingly random output bytes. And it has this property that if you flip one bit, then you get a totally different distribution of zeros and ones as the output. And you can't create, let's say, you can't come up with some random output and then reverse it and then go back to the input state. Okay, so now we have that under our belt. How do we then create these blocks? So basically a Bitcoin block contains, there's a header of 80 bytes, has some various fields, and then there's a payload of transactions. So in the header, we have a reference to the previous block, and references in Bitcoin are hash values, basically. So I can calculate the hash of my header by doing SHA-256 twice on the header bytes, and that would then be the reference for this block. So if I want to reference another block, I then put it into the header as the previous block hash. So and this sounds easy, right? So I just put in this hash thing, and then the version and stuff like that. And I'm all good. But that's a catch, because your hash value has to have some properties. And basically, when you want to create a block, what you do is you create your header, and then you have a nonce, where you put in some random data, and then you calculate the hash. Then you regard the hash as an integer. So the hash is those 32 bytes. So if you regard that as an integer, then there's a rule saying that, well, when you look at it as an integer, there has to be some, it has to be below some certain value. So that basically resembles that you should have a number of 0 bits in the beginning of your hash. And because SHA-256 produces random output, then the probability of having the first bit 0 is 50%, right? And the same goes for the next bit and the next bit. So you multiply those probabilities together, and then it quickly gets very, very hard. So for instance, the 440,000th block, which is fairly recent, to calculate that, the network had to, in total, do something like 2 billion gigahashes a second for 10 minutes. That's a large number. So it's, 2 billion hashes a second for 10 minutes. And that's a lot. So, so this is kind of the average which is necessary for calculating a block today. But it hasn't been like that since the beginning, because when Bitcoin started out, there was maybe just 1 or 2 computers running the network. And of course, nobody would be able to calculate that many hashes. So for that reason, the difficulty it changes over time. And it does that depending on how much computing power is in the network. So this graph here shows a small snippet of the difficulty over time. So basically the red bar shows that this is the minimum difficulty that you have to hit in order to solve a block. And the blue line is then the actual hash power measured during that period. And the way that this happens is that all the computers in the network, they see all the blocks, and they can then see that, well, after 2016 blocks, they will go back and they will see how long time did it take to calculate those blocks. So if it was faster than 10 minutes on average, well, then we need to make it more difficult, right? And if it was slower than that, we need to reduce the difficulty. And so far, the difficulty of finding blocks in Bitcoin have gone up a lot, because there's an incentive to mine, because you get those Bitcoins, right? So so basically, mining started by using your processor power. So 1 CPU, 1 vote, or 1 chance to find the block. Eventually, people found out that you could actually use your GPU for mining, because it's much more efficient at calculating SHA-256. And today, it's special purpose-made chips that do this. And mining is today done in big data centers, and there's no point in trying to mine a block with your own computer, even if you have free energy. Okay, so let's say that we now have calculated this block, and we want to send it into the network. So basically, you want all the nodes in the network to see your block. So you basically just, if you imagine that this is kind of a network of nodes, and then some node finds the block, and then it slowly propagates into the network. And that takes time. So because every node has to validate that the block is correct, you meet the difficulty target, and all of those things. So basically, since this takes maybe 1 or 2 minutes or something, and they appear about every 10 minutes, so then there's a probability that we will have 2 different nodes finding a block more or less simultaneously, and they will then compete to race across the network. So what happens in that scenario? And basically, what happens is that we have a fork, because we now have 2 different blocks that have a solution for the next block, right? And which one is then going to win? So this is kind of a split brain problem. And the rule in Bitcoin is simply that the largest chain wins. So basically, if you want to get the reward, then you want to be on the largest chain, because the shortest one doesn't get a reward. So basically, this gives you the incentive to continuously work on the first block that you see that is extending the chain. And basically, some nodes will see the top chain first, and other nodes will see the bottom chain. And we don't really know who wins, but you just start mining on what you saw first. And then eventually somebody will find a block, And if you are on the right chain, then, well, you'll just continue mining on top of that one. But if you are mined on the other one, then you will still want to go back to the longest chain, because the probability that your chain will win is a lot lower. So these forks, they happen all the time. Well, all the time. They happen like maybe a few times a week. And very rarely we see them longer than one block. But it happens. Okay, so basically, to sum up distribution of funds. So the funds, they are distributed by solving these blocks. The difficulty adapts over time, and the longest chain wins. So this is how money is then introduced into the system. So this is just to distribute money. We also want to transact on it, and it's not everybody who is a miner and who wants to do this stuff. But maybe just wants to send transactions. So let's take a look at that. So before we can do that, we need to introduce a few things. So in Bitcoin, we have public and private keys. So the private keys are the ones that allow you to send Bitcoin, and the public keys are then used as a proof when you make your signatures. So Bitcoin uses elliptic curves. They are shorter than RSA keys, and basically in Bitcoin we have 32 random bytes is a private key. Almost all 32 random bytes are private keys. There are some exceptions, but you can basically just come up with a random set of bytes, and that's your private key. Just have to make sure that it's not predictable, because then they can steal your money. So a public key can be computed from a private key, and in Bitcoin there's no encryption. Some people say, yeah, encrypted money, but it isn't. There's only signatures and no encryption in Bitcoin. So so the next thing we have to introduce is Bitcoin addresses. So Bitcoin addresses, they are a little bit like a bank account. They just look a little bit different. And you can calculate a Bitcoin address from your public key by applying two different hash functions. And you can generate as many as you want, then nobody really knows who owns which addresses. When you send transactions, you don't reveal that this is the name and the address and so forth of the recipient. You just say that, well, I send this value to this address. So let's try and build a transaction. So if I, for instance, wanted to send so transactions, they have inputs and outputs. So on the input side, you specify the coins that you send into the transaction, and on the output side, you specify where the money should then go. A transaction has a hash also, just like a block has it, and that's basically the SHA-256 function applied twice on the transaction data. So let's try and build it up from scratch. So let's say that I want to send 10 Bitcoin. So first I create a transaction with one output, and in that I put in the value that I want to send, and also the Bitcoin address of the recipient. So far so good. So I also need to put funding into the transaction. So on the input side, I will then put in references to transactions that have sent money to me earlier. So for instance, here I put a reference into a transaction that sent me 5 Bitcoin, and another one that sent me 3, and another one that sent me 4. So basically those 3 outputs were sent to me. The other ones were not for me, so I'll just reference the one that I can pay with. And basically the reference is actually the hash of the transaction that sent money to me, and then the output index. So in this scenario, it would be the hash of this guy, and then index 0, because that's the one that has the 4 Bitcoin, which is for me. So now I have on my input side, I have 5 plus 3 plus 4 Bitcoin, and that is 12 Bitcoin. And that's a little bit too much, because I only want to send 12. So how do we do that? So basically, I put another output that sends the remaining 2 Bitcoin to myself. And it's a little bit like when you go to the bakery and you buy a bread and you have a $10 bill, you pay for the bread and then you get some money back. So you can't do a partial spending of a transaction output. You have to spend it all. And then there's one last thing, which is basically that we want, and that's part of the incentive system in Bitcoin, is that we put in a transaction fee so that it's more likely to be picked up by a miner and put into a block. We will see that a little bit later. So, but basically to pay a transaction fee, I basically subtract a little bit from the output that is sending funds back to me. And this way, by having a difference between the inputs and the outputs, I specify my fee simply by having that difference. So in this scenario, I pay 0.0001 Bitcoin in transaction fees. So we are almost done. The next thing is then that I want to provide a signature that proves that I can spend these coins. And in this scenario, I have a reference to a transaction output of 5 Bitcoin. And in that output, there's also the Bitcoin address that can spend the coins. So basically what I put in on the input side is I put in my public key, because my public key can then be turned into a Bitcoin address, and we can show that you can only create that address if you have that public key. And then the next thing I put in is a signature that is created with my private key on the transaction. And together with the public key and the signature, you can then verify that this public key, which is the address in the output that I'm trying to spend, can be verified to have created that signature. So I repeat that for the outputs, all 3 of them, and then I send it into the Bitcoin network. So basically my Bitcoin software is connected to a few other nodes. And then my transaction will propagate from node to node until it has kind of been seen by all the other nodes eventually. And every node along the way will then verify that the signatures are sound, that the inputs that I'm trying to spend are unspent, and verify that I'm not spending too much money, more than what is on the input side and things like that. And then we relay it to the next peer. So eventually, my transaction will end up at a node which is a miner, and a miner will basically then say, well, I want to find the next block. First of all, a miner can put in a special transaction, which is the first one. This transaction is where the miner gets his reward. So the miner would then put in, I send the reward, today it's like 12.5 Bitcoin, to an address that I own. And then on top of that, the miner can choose to pick any transaction, sometimes 0, sometimes as much as fits into a block. Pick one transaction and put it into the block. And once the transaction payload is kind of filled, there's a limit which is about 1 megabyte for a block. Then he will start to see if he can find a solution for the block. So basically, you calculate what is called a Merkle root on the transactions. So it's basically a SHA-256 of all the transactions. You put it into the header, and then you start trying to change the nonce, and then calculate the hash until you eventually find a hash value which is below the difficulty target, as we talked about earlier. And you continue to do that until you find a solution, and then you publish a block. So the reason why we had this fee before, I could add this fee to my transaction, is that this is an incentive for the miner to pick up my transaction and then put it into a block, because the miner is then the one who gets the fee of 0.001 Bitcoin, and he can add that to the output value that he sends to himself in this transaction. So basically that's all fine. So my transaction has been put into a block, and the block has been propagated, and everything is good. So, but there are these scenarios where we have these forks in the network. So let's try and revisit those. So basically, it could be there could be a situation where 2 different miners, they have created a block, and both of them contain my transaction. And well, from my point of view, I don't really, it doesn't really matter, because one of the chains will eventually win, and my transaction is in both of them. So in that scenario, everything is just fine. So it could also be the case that my transaction is only in one block and not the other, and eventually, well, in one future, my transaction was not, confirmed, and in the other it would be. So that could be a little bit worrying. But basically, what will eventually happen is that one of the chains will win, and if it's not the one where my transaction is, then the next miner, could likely, include my transaction there, right? So because my transaction hasn't happened in the other future, so eventually a miner will pick up my transaction and put it in, provided that I have paid a fee that incentivizes the miner to pick it up. So if nobody ever mines a block and puts in my transaction, then my transaction just never happened, and I could then send out a new transaction with a higher fee and then get my transaction confirmed eventually. Okay, so with that kind of done, let's go and revisit some of the properties that we talked about earlier. So I said that there was no counterfeiting. So I said that, well, nobody can increase the money supply at will. And that's almost true. So, but basically, you can of course increase the money supply by creating more blocks, right? So if you have a secret recipe for calculating SHA-256 faster than anybody else, then you would be able to add more value to the currency. But basically, you are competing with the biggest distributed computer in the world, and there are many miners trying to solve these blocks. And maybe you would succeed for a short time, but then the difficulty will just get higher, and you would be back to 10 minutes a block again. Another thing is the transaction irreversibility. So basically, if I wanted to buy a fancy car or something, I could create a transaction, so the red one up there, and then send it out into the network, and then wait for somebody to try and confirm it. And when the block at the top confirms, then I would get my car and drive away or something. And then in secret, while this all happened, I would then be working on producing some blocks of my own. So let's say that I have then, while we waited for the other block to confirm, I have created 2 other blocks, and then put in a transaction that spends the same outputs that were sent to the car dealer, but sent them to myself instead. So if I successfully could do that, then I would have reversed the transaction. So the problem is, though, that it requires what we call a 51% attack, so you need to have more mining power than the rest of the network combined, because otherwise you wouldn't be able to make a longer chain. And the incentives in Bitcoin kind of say that, well, if you try to do that, then let's say that you have like 20% of the mining power. You could be lucky and create a longer chain with just 20%, but the probability that you succeed is not so high, and you would actually lose your rewards if you fail in doing so. So if you fail to make a longer chain than the others, then your mining power is kind of wasted. So therefore, the incentives kind of make you do the right thing. And apart from that, it's also quite hard to have a lot of mining power, because it's computers and electricity and everything costs money. Then the third property is the no double spending. And that's simply not possible in Bitcoin, because if you have a history where some coins have been spent, then the network will prevent you from trying to spend them again. So if you create a transaction that points to the same outputs, then no miner will pick up the transaction, because the block would not be valid. And even if I mined the block myself, then the network would reject my block, because it doesn't follow the rules. And nobody wants to build on top of a block that is not valid. So you can't double spend in Bitcoin. So that's kind of the all of the technical things with how blockchain technology works. And blockchain technology in general is pretty new, and in many ways what you have is a trustless, decentralized ordering of events. At least that's what I often call it, because you have all this long history and you can actually put stuff in there and then prove that things, they existed at some point in time. So for instance, let's say that I want to have a timestamp on a document that I wrote. I can calculate the hash value of that document and then put it into the blockchain, and I can then prove that this document existed in this point in time without having a notary or somebody else, putting a rubber stamp on it or something. And yeah, there are many different use cases for using blockchains. One of the early ones is Namecoin, which is a decentralized DNS basically. So this is a system where you can say that, well, this name, I want to associate some value. This could be an IP address or something else. And with Namecoin, you have a different blockchain. So it's not Bitcoin, it's Namecoin, where you can mine blocks and earn Namecoins. And by paying Namecoins, you can then put key value pairs into this database, which is pretty interesting, I think. Another example is colored coins. So what they are doing is that they allow you to issue tokens on top of Bitcoin, and you can then transfer those tokens from one address to another. And basically you could do that for trading assets like stocks and things like that. So another interesting example. So we have also seen other kinds of blockchains where you do more advanced stuff. There's one called Ethereum, where you basically have a Turing-complete language that you put into your transactions, kind of. So basically I can create a small piece of code which can do financial, which is basically a small financial application that I can put into the blockchain. So this code is then executed on all the computers in the network, and I can send and receive value with this program. And basically, like half a year ago, the first, what is called a digitally autonomous organization was created, which is basically a piece of code that people, they could invest in. So they could send Ether, which is the coin in Ethereum, so they could send Ether to this organization and buy shares of it. And once you had shares, you could then vote for what this organization should do. So that could be, for instance, that the organization should invest in something or do all other kinds of things. And that was really interesting to track, what happens there. And it immediately got super popular until a hacker found a bug in the code of this organization, and then took a third of the money or something and ran away. So it's not always. So it's pretty interesting that we can have programmable money, but it's also dangerous. And basically, I think, when I started looking into Bitcoin in 2011, I thought that, well, this is super interesting. Let's see what happens in the next 3 months. And it's still the same 5 years later. It's a very interesting field, and I think that for some of us, it could be interesting to have this blockchain tool in our, in our bag, and we can take it out and use it for different things, just like we use Quicksort and other things. So if you want to know more about Bitcoin, I can recommend this book called Mastering Bitcoin. It covers, everything in great detail. I think that's a really good resource. So with that, I'm kind of done. I hope you enjoyed it. And are there any questions?